All right, so good morning. We're going to be finishing up our topic from last time, and we have to talk a little bit about the GCD test. So we were talking about loop unrolling, and we were talking about software pipelining and some of these other tools that are out there. And, you know, we kind of gave the impression when it was going on that you can unroll a loop as much as you want. And that's not, well, I mean, in one sense, it's obviously true. You can run it in sequence as it goes. But you don't necessarily get a benefit. You might not be able to parallelize past a certain point. And the key with what the example I was using last time was there wasn't what's called a loop carry dependence. So here's where the loop carry dependence goes. Imagine for a sec I was, say for instance, like a for loop. And I equals 0, I less than n. Plus plus, and then I want to do something like I plus 1 is equal to twice AI, whatever. Not saying that this is necessarily a wonderful thing to do or an important thing, but imagine I had one where I was calculating a later version inside the same array with an earlier one. And in this case, I'm calculating the next one. Now, when I unroll that loop, it'll look like, because I'm doing memory access, it'll look like there's no connection between them. So I'll get my, load word for this, and I'll get a store word. But the next load word that comes in, while it will look like I can just load it, because it's loading from memory, and we didn't check if there was a dependence through there, that load word is actually going to be loading what the previous one stored. Because when I is 0, this will be storing to 1. So when this goes to 1, right, this one is of necessity going to be, needing to get that value. So if you, don't give it enough time that goes on, you're going to be stuck. And I'm actually carrying it through memory, which makes it really, really slow on the update when it goes in. So that'll really ruin my ability to be able to unroll the loop and get something good, because I just can't pack it. Some of it's actually by the way in which I'm doing that thing. It would be smarter not to put this to memory, and then it would be apparent that I was using that particular register with a read after right through the loop. Right, so the key thing is when you're looking at the code on there, and we kind of did our what was the data dependencies, there's also a data dependency going from the end to the beginning. It's not like it just ends there, and you have to look at those. If it's in a register, it's easy to check. Right? You wrote something at the end of the last loop, you're reading it at the beginning of the next, obviously that's going to be done. If I'm doing something like at the start of a loop, I'm saying load word, to whatever, T0 from 0, T1. So if I'm doing that at the start of the loop that's going on, and then at the end of the loop, I've got a store word, T0, and then it branches back up, right? And there's stuff in between, potentially even incrementing T1. It's pretty obvious that I'm using the same address that's going on. So it's easy to see, oh, this is going to carry through, and I could have the add I. Right. So there's my I plus 1, because T1 is holding I. So that was I plus 1, so this is actually an I plus 1, but that'll be I plus 1 again. So you can look at that and you can determine it. I can even have a computer look at that and determine it, because that's a nice obvious pattern. But the challenge comes in, so those ones are easy. We don't need a special test for it, you can determine it. But what do you do if I'm doing this? And now I tell you that, for instance, here's memory, and A is a pointer to that spot. And A covers that whole little section right there. But technically arrays are just organized by pointers. So, what do you do if B overlaps A? It's theoretically possible. All right? At that point, you're kind of getting into some more trouble that's going in. Now, it's theoretically possible, it's not the best programming practice. So we could say I can avoid people doing that overlapping arrays because you shouldn't overlap your arrays. It's possible. So I can't rule it out, so that's always a little bit of a danger. That would also be almost impossible for you to tell. You'd have to resolve the pointer arithmetic, and that's a bunch of calculations, and by the time you did that, you've probably wasted all the time anyway. So you're probably not, in order to put the safety check in there, you're probably not going to be able to resolve that. But I could also run into a case, what if I go to A here, but now I do something else, that I have little a times I plus B, and C times I plus D. So now I'm accessing the same array, but I'm doing some calculation for how I'm getting into there. And I could use I could even potentially have some other thing, J or whatever else, but let's just stick with I for the moment. I'm going on there. And I just have some other different thing, an order in which I am calculating them. And we do that all the time, because that's a generalization of the first one that I did. But what if I'm doing a stride where I'm doing every other one? Now when you go to parallel programming, you often will do things like take a stride of every other one. Because think about it for a sec when you're, maybe I'm summing up an array. And if I want to add together an array, whatever, 1, 2, 3, 4, 5, 6, 7, we'll just make an array with 8 items. Let's say I wanted to sum those 8 items up. Now I could walk through, and I could load the first one and go 1. 1 plus 2 gives me 3. Add that one, that gives me 6. I could walk through. Now what would be the time complexity of doing that? The big O of n. So if I kind of walk through where it goes, could I parallelize that easy? Right? I mean, just doing the sequential add. It would look like I've got a dependence that's going straight through, but do I have a dependence? I mean, there's a little bit. Anybody think of a better way of doing it? Well, I could go together and I could, what if I added those ones? And then I could add those, and I could add those. Faster? That's going on. Well, I mean, at the first thing, I got 4 processes, and then 2 processes, and then 1. It's a binary tree that goes in. So that one would add them up, and I'd get my, at the same time I do this 3 here, I'd get that 7, and I get this 11, and I get that 15, and I could get that 10, and I could get that 26, and I could get 36. Right? So, I mean, I could walk through, and if you look at it in 3 time units, I've got it, whereas here I had to take 8 time units. So it's significantly quicker to go through this way. Now, when you're looking at this type of a structure that's going on, what's the time complexity of it? Log n. So this is big O of log n. Now, is this the best way to do it? So, do you think this is even the best way to do a tree? Strangely enough, when you do this one will be good, but it'll get some weird slowdowns, particularly when you get to large amounts of memory. And the problem actually happens that you're going to get a lot of cache misses. Think about where you are loading and storing these things, right? If I add these 2 together, imagine I'm reusing the vector so that I didn't need the vector, I just needed to sum it up. And so I made a temporary copy, I did operations, now I'm summing it at the end. So I would add these 2 together, I'd stick it at 3. I'd add these 2 together, and I'd have to put it in one of these locations. because I don't want to accidentally have this process launch early and blow away one of their data values. So I kind of have to write it back into one of theirs. So I would end up with like the 3 here, the 7 there, the 11 there, and the 15 there. And then when I combine them, I'd have the 10 here, and I'd have the 26 there. Now, if you notice, they're getting farther and farther apart in their stride. So if I get a larger and larger array, they're going to be further and further away from each other. And what does that mean about cache? Right? They're going to be far enough away from each other that accessing one will not keep things in cache as well. So I'm going to be very inefficient on my caching scheme. So the problem on this type of a tree structure that's going on is it's very inefficient on cache. But I like the tree. The tree is faster. What could I do?
Traverse the tree differently.
Yeah, exactly. So imagine the same thing. 1, 2, 3, 4, 5, 7, 8. What if I did 1 and 5, 2 and 6, 3 and 7, 4 and 8? So I got 4 of them. I can store in the first location. So I've got, 1 plus 5 gives me my 6, and I can store it right there. And I've got my 2 and 6, and I can store my 8. Right? And I got my 3 and 7, I can get my 10, I can store it there, and I can do my 4 and 8, and I got my 12, and I store it there. And then I can take these and pair them up, but I'm going to do it interleaved again. So we do 6 and 10 and 8 and 12. So now the 6 and 10 is going to give me 16, and I can overwrite it into there. And I'll do the 8 and 12, and I'll get my 20. That goes there. And if you notice, what happens is it's packed. Now, in order to do that, I'm having to access my array. I got different processes running, and each of them is going to have to, we want them not to collide with each other in an earlier step, but I'm going to have different step lengths at every step. So this is, the whole reason I've mentioned this is, number one, is I think you should know about this, because it's kind of important if you're dealing with parallelism. But the other one is, you notice it comes up, the step length is, how are you striding through this process? And depending on where you go, I could have different stride lengths, or I could have different offset starts, and all kinds of other stuff that's going on between each one. And when the system sees this first level here, it's going to see that I'm doing a step of n over 2 for every one of these. So that's, my A and my C is going to be n over 2. So the question is that going to run into a problem? How does it know? I mean, we can look at this and say, is there a collision between any of these 4? No, of course not, right? But when you're looking at that, it's easy to tell, right? When you look at these strides here, can you tell whether it's going to collide or not? Well, you can. They're not going to collide, right? But how does a computer, just looking at, it just has A, B, C, D, how does it know they're not going to collide? Because if it thinks it's going to collide, it's not going to parallelize it and run them in parallel. It'll run them sequential and you'll get no benefit. So we have to make something that will allow a computer to look at this and realize that each level is completely independent of each other, so I can therefore unroll them enough to take advantage of this type of a behavior. Does that make sense? So this is kind of motivation. Why do I want the GCD test? Why is this type of a structure in the index important? Because a huge number of things like tree algorithms and stuff like that is going to have this type of an affine function that's going to determine them. Yeah.
I had a question on the different tree structure that we made. Wouldn't that still cause some cache misses because we're taking large strides? Like if the problem is really big and we take really large strides, are we going to be missing on cache, or is it just? So
strangely enough, no, if you do it well. So imagine that I've got any decent system that's going in. When I launch these, if I launch the threads in order, for instance, I could launch, like if I'm just dealing with a CPU system for the moment, let's say my system can run, say, 12 threads concurrently, right? And let's say for the moment I'm sticking each thread in a different core, ignoring hyper-threading, but the same thing would happen for hyper-threading. So I've got, n of these things running. That's a small number, 12, 16, whatever. So I'll launch, for instance, let's say like 16 of them. That's going on at a time. So I'll do the first 16, which means you'll miss on the first one in both its spots. But then every other one will hit because it'll be in cache. Right? So for each group of blocks, so for each block you'll miss, but as long as you launch them in sequence that's going on, or in concurrent groups, then they'll all hit together. So, I mean, it's not that there isn't a way to fail, it's that there is a way to succeed. And I agree, you could launch this in such a way that you would completely mess it up. But there is an easy way to launch it, which will avoid that. And that's really what you're looking at. And since the machine being very stupid and simple, the way it's going to do it is just try to launch it in sequence when it comes. And you just try to bundle them. Now, I mentioned that for course. You might say, well, what happens with something big like an NVIDIA GPU or something like that? Well, you explicitly set up warps in there, and you group them into blocks of 32, but again, I just group them together so that their whole thing loads in. And again, it's loaded now into a rapid access memory area. So it'll again work. So for the GPUs, it'll actually be even more explicitly easy. So this type of a thing is extremely important inside GPU programming when it comes down to it, because if you don't, GPUs are very dependent on being able to switch quickly between these warps and having the memory there. And so, it's possible to even prefetch and set up your memory so that they're there and everything goes nice and smooth. But you should, if you do it right, only have to load those 2 blocks in and away you go. It's a good question, and you do want to think about those. But yeah, I can actually do this in an efficient manner. All right, so we good motivationally why that cares about? All right, so now the question is, how can I tell just looking algebraically? All right, we can look at code and tell, but we're great at pattern recognizing. So what are the types of things that actually let me know whether or not I can finish? And these ones exhibit 2 different situations. Right? This one's doing small strides, right? Little steps of 1. Theoretically, it's going to run into each other. If you look at it, this has both A and C are both 1 on this, right? First, second, right? For each of those, the difference between them is 1, so the stride, the A or the C, is 1. So it's taking little small strides, but the difference is this is location 0, so that's, whatever you want to call it, C, and D is at 2. And it's doing a very short run so that the start and end happens before the next one start and end. So there's just no overlap. So even though they're taking small steps, no chance for them to hit. Do you think that's pretty easy to check? From the information that I have available. It would be pretty easy to check because I know these 2 numbers and I know how many things are you dealing with when you're adding them up. So I can take a look at those groupings that go on. I can say, how many are you pairing together? That's apparent from the code. And I can take a look from wherever I'm going into it and say, what's the start and end of each displacement zone? And how are those ones going in? So I can look at that and I can just check. I know the start, the end just takes an addition of how many entries I'm loading to add together. End of problem. That's going in. So that start and end is pretty easy to check. That's going in. But we should. So one thing we can look at, idea 1 for checking isn't unrollable when we're looking at this kind of A, B, and C, D situation for walking through the arrays. Number 1 is I can check the start and end for no overlap. And again, you might be like, well, that sounds complicated, but I can actually do you need to know what I is in order to check that? No. Right? That's true no matter what I is. So I can check that one in advance. I don't need runtime information. So that means the compiler can do that for you. So the compiler can determine without any runtime information in advance that you should do it. So it doesn't matter how much time I spend figuring this out. If I can determine this in advance without run information, I can therefore handle this through the compiler. It takes whatever time it wants, and it just gives me a good set of code sequences and unrolls or whatever. And remember, unrolling is all a pre-technique. It's a compiler technique. So I don't have to worry computationally as long as I don't need actual run information. And I don't. So that one I can check, and so we absolutely should check that. You've got the time to do it. How about for this one? The areas overlap, they just happen not to hit the same square. Okay? This is kind of like having a bunch of squares on the ground that's going in, and I'm going to walk in every third one, and you're going to walk in every third one, but if I start at 0 and you start at 1, our sequences will never match. The question is, how can I get a nice, easy test that that won't happen? Like if I had that it was 3, 0 was AB, and I had 3, 1 that's going on. Now, without worrying about the start or ends, because they are overlapping now, potentially. Well, actually, in reality they are. So if I looked at these, you know, we'll call this one the stars, and we'll call this one the pluses. So this is 0, 1, 2, 3, so on. Now, this one is a star, and I add 3 to it, so that one is a star. 4, 5, 6. That one is a star, but I've got my pluses. Now we can look at that ourselves and say, hey, I can see it. How do we take this same thing and make a rule? So have any of you done any number theory? Did you do any encryption? Anything of that sort? So you actually get underlying encryption in a lot of our security techniques is a branch of mathematics called number theory. I think a very small digression just to mention where this comes from, because I think this is kind of a lot of fun. Okay, I get sick pleasure out of this. The most pure mathematic out there to a mathematician is number theory. This is like the Greeks. And the Greeks were very big on don't taint mathematics by an application. Okay? So this is why it gives me kind of some sick pleasure out of this. Okay? So they never wanted this stuff to be used in things mathematics should be enjoyed because it's art to a mathematician. Now, it turns out that number theory is extremely applicable to computer programming, to encryption, and some of the most applicable areas inside. So, you know, in essence, we have sullied the most pure by using it. So to a mathematician, it's kind of almost like taking the Mona Lisa and using it as your tablecloth. But here we go with our tablecloth. Right? So the idea of number theory is to look at the relation between the integers, because they felt the integers were the best numbers that were going on, even better than, they didn't even acknowledge all integers because, you know, 0 was nothing, so it really wasn't there, and the negatives, you know, there is no such thing as a negative for the Greeks. This was one of the big limiters on some of their areas, so they really only dealt with 1 in bigger that's going on. And so those ones, they kind of set the discipline idea for mathematics, because they did the earliest proofs and everything else, kind of set this attitude, and number theory goes all the way back to the early Greek philosophers. But what they were able to do with it is actually pretty cool. They can prove a lot of stuff. And that's extremely useful to us. And one of them has to do with this, and they were always concerned with like greatest common divisor and how do things divide. And we use this slightly when we do integer division. Right? If I were to say 4 divided by 3, what is it? 1. right? Not, I mean, technically it's just one, it's not one remainder or anything or whatever else. But there's also for mod 3. So for mod 3 is 1, it's the remainder that's going on. Now, we look at this and we go, okay, yeah, easy stuff and things like that. But realize this remainder area is actually very unique to your number. And I can actually reconstruct the number with several of these mods. So there's actually a computer arithmetic form called residue arithmetic, which is blindingly fast. So remember how if you went through all the courses on earlier computer architecture and logic, remember that like ripple carry adders were big O of n in time, and we could go to conditional sum and it went to log n. And you could go to doing like carry look ahead and it went to 1, but it had really big inputs. And I could go to multipliers, but multipliers got really ugly now when they were trying to calculate because I was doing repeated things of the adders. So the complexity got really, really horrible when it went in. Right? If you do residue arithmetic, all arithmetic, big O of 1. Including multiplication, whatever. There's some special rules if you want to do division, right? Because you have to have, some nice results. But just think about it. I mean, I can do multiplication, or I can do, addition or whatever, and it's big O of 1, just naturally. That's really cool. So you might go, why doesn't everybody do it? The problem is, how do you get back out? The inverse from going from these to get back to your original number is complicated. So if you weren't looking at intermediate results, it would be tremendously faster. That's going on. But to get backwards, it does. So if you're interested in those, I do actually have a write-up on that inside my online notes. But it's really cool, kind of math as it goes in. This is going to be important to us right here. Because this is actually the trick of the GCD test. So if you notice, the big difference we wanted, it's actually a difference on where the starts were. But it's relative to whatever these numbers are. Right? I mean, if I had, for instance, 4 and 0 and 3 and 1, the difference is still the same. And I'd have star, there's 0, 1, 2, 3, 4, and then star, 5, 6, 7, 8, star. And if I'd start this one plus, and then you ran into each other. So it's not just the displacement, but clearly when it works, this displacement does. So it also has something to do with the fact that these two ones eventually kind of hit like a beat frequency. They clump up. The question is, how do I determine that spacing? Well, I'll tip my hat here a little bit. What's the greatest common divisor of these two? Now, I should have been hinted because it's called the GCD test. But what's the greatest common divisor of these? 3. Right? What's the greatest common divisor of these two? 1. So imagine if I always had the same number here. That's like my best situation for the stride area for separating. If I had n and n, what would the GCD be? N. But if I had, n and n plus 1, now you're in deep trouble, aren't you? So we go, the GCD is kind of hitting my basic idea of this idea of stride, and it's showing how far apart could they, because eventually the fact that it gets down to 1 tells me that there's nothing between them. Here the separation of 3 tells me that there's 2 empty spots between, so there is room that's going in. So if you consider that thing minus 1, it tells you about how far apart do they stay from each other. What's the intervening gap? And this one minus 1 gives you 0. They eventually will hit. Now, does that guarantee that they're going to hit? Yeah, no. I mean, for instance, I could have the intervals not over or not hitting each other at all. Right? but I could catch that with the first one. But what if I started these ones and the separation was huge and the other one eventually hit it, but it never got far enough along, they were so separated that they never went in. But they could overlap the periods, but just way down there, right? The GCD test will not tell you that. So this is kind of the caveat to the GCD test. When the GCD test says you're safe, you're safe. There is no problem. If the GCD test tells you there's danger, there might be danger, right? It's not a guarantee at that point. It's telling you there is the potential for danger, but you might have to check more. Just like when this one tells you no overlap, you know you're safe. But if it tells you, ooh, there is an overlap, does it mean there's danger or that there's a guarantee there's going to be a problem? No, I mean, now I do the GCD test. So there could be multiple tests that go on. So the GCD test, in that sense, is nice in which you know which side it's on, but it's a little bit too restrictive. There's a lot of other good cases you could pull out that the GCD test will flag. So what happens is with companies, they'll often make special added caveats, and they'll add extra little requirements, little things afterwards. We're going to stop at this point, but I want you to know at least where they're at. So all we have to do with this is we take, if this is A and C, we find the GCD of A and C, which in this case was 3. And we take the difference between them, right? That goes on. So I take the difference of, what do we call it, B, I'm going to do it. So we usually write it as D minus B. Now, when I say D minus B, it could end up being negative. I'm not sweating the negative sign. So you can think of this kind of as an absolute value that goes on. But we tend to mention D minus B because psychologically as humans, the second one we tend to make the bigger number, right? I mean, I wasn't even trying to illustrate this, but I picked 0 and 1, right? So it's just kind of the way we phrase it. So the bigger one tends to be later. When you're dealing with these, remember, and this is why I went a little bit on my diversion, the Greeks didn't like negative numbers. Right? To the Greeks, the difference between 0 and 1, or 1 and 0, is the same thing. It's a difference of 1. Right? They're considering what's their spacing on the number line that's going on. That's all we're considering here. So we would say as a sentence, the GCD of AC divides D minus B. What that means is that it will divide that without a remainder. Right? So it's kind of a fancy way of saying if the GCD of AC divides this, it means the remainder was 0. So, for instance, 2 divides 4. But it does not divide 5 because there's a remainder of 1. So if the GCD of AC divides D minus B, you might have a problem. Okay? That's the potential danger. Because if it divides it, it has a remainder of 0. That's saying this type of thing could happen. Because 1 divides 1. But 3 does not divide 1. So if the GCD of AC divides D minus B, you might have a problem. If it does not, you're safe. And you can unroll to your heart's content. Now, once you've determined that there is a danger, it doesn't mean you're done. Now you have to determine how many steps till it does. And that's actually not a hard problem. I can do that in advance too, because as long as I've got a nice explicit for loop where I know what the index is running on, I can just start it at the starting index and take a look at how many things to go on. And I can run that, remember, I'm offline. So I can do this in advance while you're making the code. And I can determine, oh, I can always go at least 4 times or whatever. And that tells you if I can always go 4 times, it tells me how many times I can unroll my loop. right? If it's only safe for the first one, then you can't unroll it. If it's safe for 2, I can unroll it once. So at that point, you at least know you have to do it. If it tells you you're safe, do it as many times as you want. You don't have to check anymore. Does that make sense? So that kind of gives you that introduction thing. And you know, as the ad note to, I mentioned the whole thing with dealing with number theory and the rest of that. This same idea of using modulus, because that's really how you determine this. You take the GCD of this, and you do this mod that, and you see is it 0 or not. So it's a very easy check for us that's going on. You know, it's one division operator. That same thing of that is actually how most encryption algorithms work. So standardly what you do is you take whatever you calculate, you'll get a fancy math formula, whatever exponent or whatever to calculate it. So like, you know, RSA just takes whatever your code is that you're doing and it raises to the power of your key, and then it does that whole thing mod your block. Very easy equation actually. So all you're doing is the residuals that's going afterwards. And it turns out that that is nice and reversible. And since we have all this residue arithmetic fun stuff, it's invertible and all the rest of these cool things. As long as you pick these appropriately. That's why they have to pick those fancy keys and calculate them. Is we have to check that they're mutually co-prime. It would be a problem, right? They're going on depending on where it's going in for handling them. Okay, we feel safe and good with this. So this is kind of our last thing that's going in. If you can't, right, so everybody, once they learn the GCD test, they always feel obligated to do the GCD test every time. Do I have to do the GCD test every time I want to unroll loop? I see no's. You're correct. No, you don't. When do I have to do the GCD test? Only if inside your loop you have 2 arrays being accessed using these affine equations and you have different coefficients that's in there. It's the only reason for the GCD test. What if there's no array being accessed? Then there's no reason for a GCD test. The GCD test is only used when you're accessing the same array by a different set of numbers. That's it. End of story. Right? No other reason.
We have that form of an equation inside the loop to do GCD.
Well, you need to be, the GCD test should have the same A and you should have these. Now, if I have an A and a B, right, technically what that means is the A and the B are pointers, so those are base offsets. But the question comes up, if I have an A and a B, do I know where A and B are going to be pointing to? If you do, you can take that difference as part of your GCD test and you can just wrap it into these offsets. And therefore it goes back to a single pointer and I've got my offset area. If you don't know what those are, then you're in deep trouble. For instance, imagine A and B are dynamically allocated arrays. Right? I couldn't use the GCD test. Now, as long as I am sure that those are dynamically allocated arrays and I don't overlap, somebody didn't do something horrible and make the pointers point midway through the same array, right? Then I'm okay. But realize there are cases where you want different pointers going inside. What if I want an iterator? I can have 2 different iterators walking through an array, and that becomes considered very good coding practice again, right? But iterators are just walking through the code. But the iterators should know where they're starting and ending. They should have some information that's determinable. They don't always. But the idea is that at least the iterator should have some ability to check these things. But realize you could run into those problems. If I do, and I don't know where they are relative to each other, I can't do this because I don't know the displacement. I don't know D minus B. If I don't know D minus B, I can't do it. So ideally, you either, you know, they're the same, in which case I know they're relative, or they're different and I know them in advance, in which case I know they're relative. If I know that they're completely not overlapping because they're different and they're not pointing to the same array and they will never point to the same array, then start and end, no overlap. I don't even go to the second one, which is do the GCD. You know, so if this one says I'm safe, I don't need to go anymore. It says I'm in danger, I go to the next one. If that one says I'm in danger, I go to whatever my next check is, and this is where you can get into those add supplementals. Good? Alrighty then, that covers our GCD.